Right, so for those of you in the audience who don't know me, my name is Nial. I'm a postdoc at Cambridge University, and I am visiting UCL to take part in a radar project here. And the project is about monitoring active lava lakes at volcanoes. One volcano in particular, which is Mount Erebus in Antarctica. So, there we go. This is Mount Erebus here. It's a large stratovolcano, so almost 4,000 meters in altitude. So I thought I would start off the presentation just by kind of showing you where this is. So if we go to Google Earth for a moment, here we have Antarctica. That's at the southern end of the pole for people who aren't clear. There's no polar bears in Antarctica. And over here, this is the Ross Ice Shelf here. And this is Ross Island, which was discovered by James Clark Ross back in the heroic era. You might think this looks like it's a very long way away from anywhere, but down here on this peninsula sticking out, there is basically a small city. And this is McMurdo, which is the large American Antarctic base. So Ross Island, James Clark Ross names the peaks after his ships. This is Mount Terror, and this is Mount Erebus here. So Mount Erebus, active volcano. We can see this is the caldera rim here, and then in the center of the caldera there is this cone which has two craters in it. And the interesting thing about Erebus is that in the corner of this main crater over here is an active lava lake, which is quite a rare thing for a volcano. So this is quite literally the exposed top of the volcano's magmatic system. So if you imagine the kind of cartoon of a volcano, you have some mountain underneath, there's a magma chamber, there's a conduit that comes up to the surface. And now normally, at some point in that conduit, there's an interface between the magma and the atmosphere. And in most volcanoes, this is a long way below the surface, and so you can't see anything. But at Erebus, this interface is at the surface. So if we go back to the slides, this is the Erebus lava lake. So this is what was in the corner of the crater you saw before. This is about, well, it varies from year to year how big it is, but this is something like 40 meters across. And one thing that you need to explain is what is an active lava lake. So what we're talking about here is not just a pool of lava. A pool of lava would cool off and solidify after a short period of time. This thing has been on Erebus for decades. So this is linked to the deeper Earth, and there's a flux of heat to the surface which keeps this thing molten. So the fact that we can see this lake is very interesting from a scientific perspective because it allows us to make measurements of the processes which are normally occurring deep under the Earth where we can't see them. So each year, a team of people travel to Erebus and we camp quite near the summit. This is our camp here. And if we go one slide more, you can see pretty close to the top. And we spend a little bit more than a month there normally making measurements of this volcano for this reason.
What kind of measurements do you make?
I'm coming on to that,
okay,
but yeah, a whole range. It's a multidisciplinary team who travel there. So up at the crater rim, we have spent the past few years working a lot to try and improve the infrastructure there for making measurements. So now we have mains power coming up a cable from a power generation site lower down. We have relatively high-speed Ethernet from a wireless system, and we're gradually installing permanent instruments. So this one here is a thermal camera, thermal infrared, which is looking at the lake and recording year-round, or as close to year-round as we can get with power requirements. So I'm going to show you a little bit of data here from the infrared camera to show one of the things that we're specifically interested in about this lake. So this movie sequence here is the raw thermal infrared images. These vectors plotted here are the computed surface motions from this raw image. And this plot here is showing the mean surface velocity with time. And as you can see, there is this very regular periodicity in the surface velocity. This spectrogram at the bottom shows this band of periodicity across the sort of 600 to 900 seconds range, so 10 to 15 minutes. The surface of the lake is speeding up and slowing down, speeding up and slowing down. And this is incredibly regular, and we observe this every year. So for tens of years, the lake has been doing this very, very oscillatory motion. And we believe that what we're seeing here is a surface manifestation of what's occurring in the conduit, which is feeding this lake. And so we're interested to try and understand this process to enable us to infer what mechanisms are driving the lake.
In what direction do you mean it's moving? Is it up and down?
This is lateral motion. So as you see these cracks move across the surface of the lake here, it's being tracked by a feature tracking algorithm. And so it's lateral motion. But, okay, sorry, we'll come on to that in a minute. As well as the surface motion, which is shown in black on this plot. So again, you can see very oscillatory. The blue trace is think of it as the composition of the gas which is coming out of the lake. So in magma, there's a huge amount of gas stored in solution. So think of it as like a bottle of Coke. There are no bubbles visible in the bottle of Coke, but as you take the lid off and you depressurize it, suddenly all these bubbles appear. And magma is exactly the same. There's all these volatiles in it. As it ascends towards the surface and the pressure is removed, bubbles form and they rise out and you get gas coming out the top. And the composition of that gas that you see depends on the depth, because the different species of gases have different solubilities. So some will come out of solution much deeper down than others. Carbon dioxide being a good example, that comes out of solution very low down. Sulfur dioxide comes out much closer to the surface. And so by measuring the ratio of carbon dioxide to sulfur dioxide, you can tell where the gas which is being emitted came out of solution. And so as well as the motion going up and down, as well as the surface velocity going up and down, we see the composition of the gases is also varying, and it's varying with exactly the same periodicity, and it's very highly correlated. So whatever process is driving the oscillatory motion on the lake is also driving a change in gas composition. So again, at the crater rim, this is the thermal camera I showed you before. This is a Fourier transform infrared spectrometer, which is what we're using to measure the gas composition. And this is a LiDAR, which we've used a few years to take high resolution point clouds of the surface of the lake. And if I show you a video of the LiDAR data from 2012, this is the lake here. And you can see that the surface of the lake is pulsating up and down as well. And we see that, again, this is very highly correlated with the surface motion and the gas composition which is coming out of it. The surface elevation of the lake is the cleanest signal of this pulsatory behavior that we can see, because taking the lateral motion using this motion tracking algorithm is very noisy. The gas composition is also very noisy because you get things like accumulation of gas in the crater, which skews your measurements and things like this. So this is basically the best time series that we can get in order to try and understand this. But the problem with LiDAR is that even when the weather is nice in Antarctica, often you can't see into the crater because there's too much humidity from the gases being emitted from the volcano. And the LiDAR is relying on a laser spot being able to find the surface of the lake and be reflected back to the instrument, which obviously you can't do in these kind of conditions. Even when it's incredibly clear in the crater, this is the lava lake down here, you can see there's still quite a plume rising off, and this, again, is a problem with the measurement. So in the video I showed you, you see there was lots of missing data points, and that's largely because the plume was in the way. So that brings me on to the current project, the idea being to use a radar to measure the surface elevation of the lake in order to monitor these changes. The radar obviously isn't influenced by these kind of atmospheric conditions, and so we hope to be able to get a very long, very clean time series of the surface level of this lake, which will allow us to do a more detailed analysis on the time series than is currently possible, and hopefully understand a little bit more about why the lake is behaving in this way. As well as these cycles, the lake also does this. There are sporadic explosions. It's not entirely clear why this happens, but the most likely scenario is that somewhere within the conduit there is some kind of cavity or crevice, if you like, and gas is gradually accumulating there, and then it forms a large slug which comes to the surface and causes these large explosions. And just because they look cool, we're going to go through a few more pictures. So this is the lake. This was in 2011, I think. 2 seconds later, it looked like this. Again, remember that this kind of scale across this is 40 or 50 meters, so this is quite a big explosion. And 2 seconds later again, then it looked like this. These explosions are pretty big, and they're throwing lava bombs out of the main crater of the lake, and often 200 or 300 meters away from the volcano, and in some years up to kilometers away from the volcano. So this is an impact crater on the side of the volcano from one of these bombs that came out 2 years ago. And these things are not small. So this is a bomb which landed just on the crater rim 2 years ago again. And these things are still molten when they hit the ground. So if you're quick and you run up to them, they're still hot to touch, and they're still molten in the middle. If you break them open, they're incandescent. So this is another form of behavior which we're interested in looking at with this radar, is these sudden bubble bursts, because it's not clear whether they're happening very regularly or whether it's totally random, and how they might influence this kind of passive up and down motion that we see on the lake. So the basic idea for this radar system is as follows. This is the instrument site where I've shown the pictures of before. Has an unobscured view of the lake down here. The idea is to set up a radar system here which will measure this slant range and therefore allow us to measure the surface of the lake going up and down. And the idea is to run this at something like 10 hertz, probably, measurement frequency of something like 10 hertz, to allow us to accurately pick up the passive up and down motion, and also to pick up these large bubble bursts which happen. Obviously, the problem with this from a radar point of view is that this kind of viewing angle means that most of our transmitted power will be reflected away from us and probably bounce off the wall here and come back, and there'll be lots of messiness in the signal processing. But the idea is to use a kind of correlation analysis to improve our range resolution in order to get better than what would normally be achievable. At the moment, we don't really know how well this is going to work. It's a sort of suck it and see kind of project. We're going to try and have a prototype of the radar built by Christmas and take it down to Antarctica this year, take some measurements and see how well it works and what it looks like. As well as the kind of physical problems, there's also the weather to think about. This is the thermal camera after its first winter over in Antarctica. It's pretty iced up, and for people who are looking carefully, it's also pointing in the wrong direction. The lake's over here. So the wind loading on this was enough to bend a 5mm stainless bolt and twist the camera around. So the radar system is going to have to be pretty well put together in order to survive the winter. I think that's probably me said enough that you will realize that I've got no idea what I'm talking about. So if anybody has any questions or comments, then you're free to ask them or email them to Matt, and he can probably give you a better answer.
How directive do you want the antenna to be now for that geometry? You had the diagram set up.
Yeah.
Will that help you try and avoid some of these problems?
As directional as possible. So we're looking at a few degrees beam width.
Right, okay.
And, well, as I've spoken to you about it, alignment is going to be a problem. So we have separate transmit and receive antennas. as you can see from some of the pictures, the visibility in the crater is often very bad. Trying to align, transmit, and receive with such a narrow beam width onto a relatively small target, I think, is going to be very challenging.
So is it an FMCW radar?
Yes, it is. Yeah.
Relatively high frequency.
Yeah, 10 gigahertz is what we're looking at. Yeah.
And what sort of polarization you are looking at, or dual polarization?
That's a good question. Matt, you can take that.
I have no idea.
I mean, is it like well known? I mean, the lava is well known, like kind of structure, or does it changes? If it doesn't change, it's better to go to dual polarized thing, maybe, or polarimetric,
Okay.
as you can gather as much as data as you can about that.
I think it might be more trying to avoid the clutter that isn't the lake. So, I don't know, horizontal might be better marginally, I'm not sure.
I'm not sure what information polarization would give you.
Yeah.
What it would help with.
Yeah, so I think just try and minimize clutter by purely rotating the antenna and seeing which is best. I would have thought.
Yeah.
So you're on the side of this volcano in your tent. You're not worried about one of those lava bombs hitting you?
At the camp, we're far enough away that it's not a problem. The camp actually used to be sort of up around this bit up here, and it was within walking distance of the crater. And one year they turned up at the camp and they found an enormous bomb right outside the hut that was still steaming. And so after that they moved. So we're now about 2.5 kilometers from the top. So no great risk to us here. But certainly when you're working up in this top part, it's something to keep in mind. And
But it never happens like while you are standing around it, or?
Yeah, of course. It's happened a few times. It's pretty scary when it happens. I mean, it's phenomenally loud. And the protocol is basically you watch where the projectiles go, and you try and step out of the way if they're coming towards you.
Easy.
Yeah, easy.
So not run.
No. It's best don't run away because they're traveling much faster than you. But yeah, stand and look up, step out of the way. Everybody wears climbing helmets, but I don't even know why. I mean, you saw the size of that thing. Helmet's not really going to help you.
Like duck and cover.
Yeah, exactly.
Is there any chance the volcano will erupt or anything like this? Full eruption, or is that not this type of volcano? I don't know much about volcanoes.
Not really. I mean, it has in the past. There are lava flows down the sides, which are, is it 10 or 100,000 years old? I don't know, pretty old anyway.
Yeah.
And there's also tephra deposits around Antarctica, which are thought to be from Erebus. So it has had more vigorous activity in the past. But I mean, it's been doing this for a long time now. Basically, while the gas is escaping pretty much unhindered, there isn't a big increase in pressure happening. It's always possible, and that's one of the reasons for monitoring it, of course. As well as these kind of detailed observations of the lake, we're also doing things like GPS deformation and seismic monitoring. And yeah, if we suddenly started to see the area inflate, then we might be worried, but it's not really happening.
Any other questions? No? Okay, thanks, Niall.